Hello, today I will be presenting our paper Breaking the Quadratic Barrier for Matrix Intersection. This is a joint work with me, John, Sagnick, and Donapon. So let's start with a summary of our results. So we provide the first subquadratic matrix intersection algorithm using independence quadratics. The previous best used a quadratic number of queries. We provide two algorithms, one using n to the 9/5 and one using n to the 11/6, depending on whether we can use randomization or not. How we do this is that we note that previous work lets us focus on a specific graph reachability problem. And for this graph reachability problem, we give a new and simple subquadratic algorithm for it. For this reachability problem, the previous best was a quadratic number of queries, and ours is either n to the 3/2 randomized or n to the 5/3 deterministic. So let's start by defining what a matrix is. So a matrix is a set of elements, V, where we say n is the number of elements, and together with the notion of independence on this set of elements. This notion of independence must satisfy two properties. The first one is a downward closure, where if some element is independent, then any subset of it is independent as well. The other property is the exchange property, where if you have two independent sets and one is smaller than the other, then there always must exist some element which you can move from the larger independent set to the smaller independent set while still maintaining independence. So the two most classical examples of matroids are the graphic matroid and linear matroid. In the graphic matroid, we have some graph, and the edges of the graph are the elements of our matroid. And our notion of independence will be that we say that a set of edges are independent if they induce a forest or an acyclic subgraph, like the orange set of edges here in this example. The other example is the linear matroid, where we have some matrix over some vector space, and the elements of the matroid are the row vectors, and the notion of independence is normal linear independence. The specific problem we have solved is that of matrix intersection, where we are given two matroids on the same set of elements, but with two different notions of independence. And the goal is to find some common independent set, that is some set which is independent in both of the matroids at the same time, and we want the set to be of maximum size. One thing we have to discuss is how do we actually access these matroids? These notions of independence can be quite arbitrary, so we need some specific way of accessing the matroids. And we use the classical independence oracle model, where we are allowed to ask independence queries. So we can specify some set of elements X and ask whether it's independent in either of the matroids. I also want to note that the intersection of three matroids turns out to be NP-hard. So let's look at some examples of matrix intersection. Matrix intersection models many combinatorial optimization problems, among them being bipartite matching, finding arborescences or directed spanning trees, finding colorful spanning trees, tree packing, and some graph orientation problems, and more problems as well. So let's look at the bipartite matching case as an example. Here, the first matroid will say that looking at only on the left side, we use at most one edge per vertex. And the second matroid will be looking only at the right side, we use at most one edge per vertex. So some set of edges which is independent in both of these matroids will correspond to a matching in the graph. And a maximum common independent set would correspond to a maximum matching. Matrix intersection is also related to submodular function minimization in that it is a special case of SFM. So understanding matrix intersection better can help understanding SFM better. Let's take a brief look at a history of matrix intersection algorithms. So the first polynomial algorithm is due to Jack Edmonds in the 1960s. And by a series of papers by Edmonds, Lawler, and Eichner Dowling in the 60s and 70s, we can pin down an n-cubed query algorithm for matrix intersection. This algorithm is inspired by bipartite matching algorithms. Recall that bipartite matching is a special case of matrix intersection. So these algorithms are based on finding augmenting paths in what is called the exchange graph of the two matroids. So in 1986, Cunningham gave a faster algorithm, now using n to the 2.5 queries. And this is again based on finding augmenting paths in the exchange graph, but now we borrow some blocking flow ideas from the Hopcraft-Karp bipartite matching algorithm. So in 2015, Lee, Sidford, and Wang was the first one obtaining an n-squared query bound on matrix intersection. And how they do this is by a general cutting plane method for convex optimization problems. So this is no longer based on the augmenting paths algorithms like before. Quite recently, in 2019, there were two independent works, one by Chakrabarty, Lee, Sidford, Singla, Wang, and the other one by Nguyen. And they were concurrent and independent, and they both showed an n-squared algorithm for matrix intersection based on these augmenting paths ideas again. And essentially, this is an efficient implementation of Cunningham's algorithm from 1986. So what we can see here is both that these cutting plane methods and these augmenting path methods are currently both stuck at this quadratic barrier. They run in n-squared number of queries. So this is the major open problem we have been attacking, whether we can break this quadratic barrier. So there have been some recent progress before our paper on this. So firstly, the Chakrabarty, Lee, Sidford, Singla, Wang paper in 2019 showed that you can break the quadratic barrier if you are allowed to use the more powerful rank oracle queries instead of independence oracle queries. I'll just quickly define what rank queries are. So instead of like in independence queries, we ask for a set X and we see whether it's independent or not. In rank queries, we ask for a set X and we get back the size of the largest independent subset of X. And there's also been some more progress towards breaking the quadratic barrier, again by the CLSW paper. And they show that you can break the quadratic barrier in the approximate case. So if you only need a 1 minus epsilon approximate solution, you can get a subquadratic number of queries. And this is again using independence queries instead of rank queries. Our contribution, as you might have guessed from the title of this presentation, is that we can indeed break the quadratic barrier in the classic independence query model for an exact solution instead of an approximate one. And we show a randomized n to the 9/5 independence query algorithm and a deterministic n to the 11/6 independence query algorithm. So the deterministic algorithm is slightly less efficient, but still subquadratic. So let's move on to a rather quick proof outline of our algorithm and how we obtain this subquadratic matrix intersection algorithm. So we focus on this reachability problem, where we are given a graph, a bipartite graph, which is directed, and it has bipartition L and R. So we have two sides, the left and right side. And we also have two special vertices, S and T, or the source and the sink. And the goal is to find some ST path in this graph, like the one marked in orange here, or determine that no such path exists. So the catch here is that we do not know the edges of this graph. Instead, we can only access it with some specific queries. These queries are like this. You specify a single vertex on the right side and a subset of vertices on the left side, and you can ask whether this vertex on the right side has some in neighbor from this set of vertices on the left side, or some out neighbor from this set of vertices on the left side. So let's look at an example here. If we specify this vertex here and this set X here, we would obtain the answer yes if we ask for whether B has an in neighbor from X. While in this case, we would obtain the answer no, because we specified some set X here with no edges. So It turns out that this reachability problem is related to matrix intersection. In particular, finding an ST path would correspond to finding an augmenting path in this augmenting paths framework by Edmonds. So, and also these queries corresponds to independence queries in the Matroid. And we show in our paper that if you can obtain a subquadratic algorithm for this reachability problem, then you also obtain a subquadratic algorithm for Matroid intersection. And the idea to do this is that we used a recent subquadratic approximation algorithm due to CLSSW to find many short augmenting paths. And to the remaining very few and very long augmenting paths, we can use this subquadratic procedure for this reachability problem. So let's for now focus on this reachability problem, and let's make a first try and see why it's difficult. Say we would try to implement some standard graph exploration algorithm like breadth first search. So say we have so far found some set of vertices which are reachable from S by doing our breadth first search. We find these different layers. Note that they will alternate between the right and left side because the graph is bipartite. So say now we have found that these vertices in R are reachable from S, and we want to continue our breadth first search by finding the next layer. Here, we can simply ask our queries where we specify one vertex on the right side in R here, and some subset of vertices in L. This is the allowed queries, and here we want to use the out neighbor query. And here we can indeed efficiently find the neighbors by a binary search idea. So we split this X up into two approximately the same size parts and then recurse on them as long as they have an edge from V. And we can find all out neighbors of V in log n queries per out neighbor. This is essentially the idea which lets the two recent papers from 2019 implement Cunningham's algorithm in n-squared queries. So let's look at the other case when you move from L to R instead. So again, we have some vertices which we have already found are reachable in our breadth first search. And now we have the current layer is in L, and the next layer we're trying to find will be in R. The problem here is in the asymmetry of the queries. For the queries, we're only allowed to specify a single vertex on the right side while a set of vertices from the left side. So here, clearly, the best you can do is go through all the vertices on the right side to query whether it has an edge from the set or not. But this can need up to n queries in total, or all of the queries on the right side here. And since you need to do this for every other layer in the breadth first search, this will be an n-squared query algorithm. And this was the state of art before our paper. So even finding a single augmenting path in Matroid intersection, there was nothing better than n-squared to do it when the path was long. So the question is then, can we do better and solve this reachability problem in some better way, specifically in a subquadratic number of queries? And so our idea is a quite natural one. We split the vertices up into heavy and light vertices. Again, we look at the case where we have some vertices which are reachable from S here. And we are in this tricky case where we got stuck before when we tried to move from a layer in L to the next layer, which we don't know yet, which will be in R. So we look at the vertices in R here and classify them as either heavy or light. So we say a vertex is heavy when it has large out degree, and the vertex is light if it has a small out degree. And when we say out degree here, we mean to the rest of L, the vertices in L, we do not yet know whether they are reachable from the source or not. And this is useful because if we can discover that some heavy vertex is reachable here in the next layer, say we are lucky and we find this edge. So in the next layer includes one of these heavy vertices. Then in this lucky case, we are really happy. Why? Because in the next iteration of the breadth first search, we would find all of these neighbors of our heavy vertices of our heavy vertex, which there are square root n many. So this can only happen n divided by square root n many times, which is just square root n times. However, what if we are not as lucky and we don't find some heavy vertex? Say there only light vertices will be in the next layer here. Then we don't make enough progress and we still need to query all of these to find whether they are in the next layer or not. So our main insight is that we can still efficiently find a heavy vertex, perhaps by jumping through several edges instead of just a single one. And how we do this is by a procedure we call the reverse breadth-first search. Our first thing we note is that the light vertices only have few outgoing edges. So we just find all of them. And we can do this with this binary search trick as before. And then we will start a breadth-first search from all heavy vertices working in the reverse graph. So going backwards and try to find some heavy vertex which is reachable from S. So let's look at this picture here. We have the set of all heavy vertices here, and all of them have large out degrees. That's the definition of being heavy. Then we try to implement the breadth-first search, going on the edges in reverse here. And when moving from a layer R to L, that was the easy case as before, where we can just use the binary search trick with the queries. So this is easy and we can move to these vertices here. Where we got stuck before was moving from L to R, but now we note that only light vertices can be here because all the heavy vertices are the roots of these breadth-first search trees. So we know all these edges already. We have already found them. So we can just traverse them without using any more additional queries. And then when going from R to L again, we use the binary search trick, and then we alternate with using these light edges like those we already know and the binary search trick until we end up with some vertex we already know are reachable from S. We can then simply trace back this path to the heavy vertex. So now we have found some heavy vertex which is reachable from the source. And this is the good case again, right? Because now we know that at least square root n many vertices, we have found square root n many new vertices reachable from the source. So to summarize our reachability problem algorithm, we run in square root n phases, where in each phase we start by categorizing vertices as either heavy or light, depending on their degree. And then for all newly light vertices, those which were heavy before, but now in this phase have turned light, we find all the outgoing edges for them. This will only happen at most once per vertex. And then we use this reverse breadth-first search procedure to find some heavy vertex reachable from the source. So in the phase, this first problem of categorizing heavy and light vertices, we do not know the degree of a vertex. So we need to do some sampling with these queries to solve this. And this is what we do in the randomized case. We just use a simple sampling procedure, quite standard, to find the approximate degree of a vertex. However, in the deterministic case, we can no longer use this sampling idea. Instead, we carefully keep track of a small list of neighbors for each vertex, which we keep updating between phases, and use some amortized analysis to show that this still leads to a subquadratic algorithm, although this is less efficient than the randomized sampling approach. I also want to note that this random sampling to categorize a vertex as either heavy or light is the only place we use randomization in our reachability algorithm, and also the only place we use randomization in our final Matroid intersection algorithm. So for the reachability problem, if we run this algorithm, the final runtime will be n squared n for the randomized version, or slightly less efficient n to the 5/3 for the deterministic version. Both of them are subquadratic. So to summarize, we solved the reachability problem in a subquadratic number of queries. The previous best used a quadratic number of queries, and we have two versions which use subquadratic number of queries, either a randomized or deterministic version. Combining this with previous work, especially with the subquadratic approximation algorithm by CLSSW, we obtain an subquadratic Matroid intersection algorithm. So this is the first subquadratic Matroid intersection algorithm. And the previous base used a quadratic number of queries, and ours use n to the 9/5 randomized or n to the 11/6 deterministic. So let's move on to some open problems related to Matroid intersection. The first problem is investigating the gap between the lower and upper bounds for Matroid intersection. Most recent papers have only improved the upper bound case, like ours. While in the lower bound case, it's still quite open to even get some omega n to the 1 plus epsilon lower bound for some positive epsilon. Another open problem is to investigate this reachability problem in more detail. We conjecture that our n squared n bound is tight, at least for the randomized case. And another open problem is to try to generalize these techniques, or maybe invent new techniques to solve the weighted Matroid intersection case, the intersection problem, also with a subquadratic number of queries. So weighted Matroid intersection is where instead of you want to find a maximum size common independent set, each element also has a weight, and you want to find a maximum weight common independent set. So our final open problem we list here is to investigate the gap between the independence and the more powerful rank oracle models. If we just look at a few problems in these models, say the reachability problem, we see that it can be solved in n squared n time by our algorithm for independence queries, but there is a very simple linear algorithm for rank queries. And also in the approximate case, we have the same kind of gap where there's an n squared n algorithm with independence queries and a linear algorithm for rank queries. And this concludes my talk. So thanks everyone for listening, and have a good day.